Good day and welcome. So today we'll be tackling a video lecture, a supplemental lecture for what we have discussed for the course Feedback and Control Systems. Specifically for the first topic for our first week, which is the Introduction to Control Systems. So this supplemental video lecture serves as an additional resource for you guys as we would be discussing some concepts in a bit more detail as compared to our discussion from our online class. The flow of the discussion would still remain the same as we would begin with a definition of a control system. Then we would be looking into the different parts of a control system, differentiate an open loop from a closed loop system, discuss the advantages and disadvantages of a closed loop system from an open loop system. And then finally, we will be looking into the control system design process. So what is a control system? What I did is I actually gathered different sources of materials to look into the definition of a control system. Even though the wordings are different, it is actually pointing out the same idea. Let's look at the first definition. So this text tells us that a control system is actually an interconnection of components forming a system configuration whose main purpose is to provide a desired system response. So the main idea of the first definition is that those components forming a system is there to actually provide a desired system response. In other words, gather a desired output using the different components formed together. Another definition states that the central idea of a control system is that there is a measurement of the system's output and have it fed back to a controller and use that fed back measurement to affect the system. The second definition actually points out to a dynamic control system which can actually react or respond rather to changes or errors in the system. But our main idea for a control system, as mentioned, is still the system's output. We want to control the system's output through the use of a controller. In the second definition, it is mentioned that this controller is actually affected by a feedback measurement. Another definition points us to an arrangement of physical components connected and related in such a manner whose main purpose is to actually either command, direct, or regulate itself or another system. So we can actually use a control system to control another system. So it either controls itself or used as a controller for a bigger control system. Now let us look into the different control feedback components. So what we're looking right now is an example of a closed loop control system, which we would define later. So it involves a reference or a reference signal, an input filter, a controller, the actuator and process inside a plant, an incoming disturbance, an output, and a sensor affected by sensor noise going back into the controller. The process itself is the main component of a control system. This is what we're trying to achieve. Through the use of the process, we can actually control the desired output or the variable of the desired output. Now, the process itself is controlled by an actuator. Depending on the type of control mechanism or control system, the actuator could actually be represented by different components. It could be a condenser. It could be a gas valve to control temperature. It could be a number of things that can directly affect the process. Now, in most cases, the actuator and the process cannot or is not taken separately, but taken as a single entity. As the actuator is the one that directly affects the process, the actuator and the process combined together is called a plant. And the plant is the one that actually produces an output. Now, in order to control the plant, we would be needing a certain type of input. But more often times than not, in a control system, the type of input is relatively dissimilar to the type of signal that would be needed to actually affect the plant. As such, an input filter is used to actually convert the reference input signal into a form acceptable by the system. Now, that reference or that converted signal is used to affect a controller, together with the signal coming from the sensor feedback. Now, it must be noted that the type of signal the input filter transforms the reference signal into should be the same type of signal used by the sensor, as they would be needed to compare to each other in order to determine what type of action the plant needs to change into. The output from the reference signal and the output of the sensor actually controls the controller, or affects the controller rather. The actuator inside the plant, or the plant itself, would not be able to change its output without any input signal coming from the controller. This controller reacts to the changes in the input and the changes from the output signal. Part of the controller actually detects and finds the difference between the reference input signal, which comes out of the input filter, and the sensor. Any differences between the two means that the desired output and the actual output are still different, which causes the controller to react in such a way to make sure that the plant or the plant's output directs closer to the desired output. We have mentioned the sensor several times already, but sensors are used to actually feed back the output back to the input where it is compared to the input signal. Sensors are used because they typically convert any variable into a form which is suitable for use by the controller. But more often times than not, these are converted into electrical signals. As I mentioned a while ago, the type of signals used as an output for the sensor should be similar in nature to the output of the input filter, as they are needed to be compared to each other to determine if the actual output has reached the desired output. Unfortunately, in a in an ideal system, or in a practical system rather, we would need to take into consideration unwanted signals or unwanted disturbances that may cause any changes to the process or the plant. Those disturbances could also affect the sensor as sensor noise, which in turn would also affect the output. A good control system is able to compensate any changes coming from the disturbance coming in through the plant. Or it could compensate any changes coming from the sensor noise, which in turn affects the signal input for the controller. Ideally, there should be zero disturbance and zero sensor noise, but it is impossible. The only thing we can do is not eliminate them, but minimize its effect on the output. Now let's try to differentiate the open loop system to a closed loop system. An open loop system has a controller that does not use any part of the output in controlling the actuator. It only uses actual input or the present input in affecting the plant and the output. Any control system that has no feedback is classified as an open loop system. On the other hand, a closed loop system utilizes additional components in the form of sensors and controllers to be able to connect the output back to the input. The good thing about the closed loop system is that any differences between actual and desired output is compensated by the feedback mechanism. As mentioned a while ago, the feedback mechanism is usually in the form of a sensor that measures the output signal and then feeds it back to the controller input, which is where it is compared to the reference input. Any difference between the two is compensated by the controller, as it means that actual output and desired output is not the same. What are the main advantages of a closed loop system? So a closed loop system is less sensitive to disturbance, meaning As I've mentioned a while ago, we cannot eliminate disturbances, but we can compensate or we could minimize its effect. Any control system is affected by a disturbance. And as mentioned a while ago, these unwanted disturbances eventually affects the output. But why is a closed loop system less sensitive to a disturbance? When any disturbance affects a closed loop system, the sensor picks up the output or any change in the output and feeds it back into the controller, sensing a difference with the desired output. And that in turn would make the controller affect the plant to be able to compensate for the disturbance. A closed loop system is also less sensitive to plant changes. What it means is that even with the existence of disturbance, through wear and tear or to continuous use, a control system or a plant also changes its characteristics as it is being used from time to time or when it is being used continuously. Gears get worn down, wires get broken, sensors get less sensitive through time, which in turn affects the final output. We cannot expect that the final output would remain the same as all components in the system changes through time. Good thing about a closed loop system is that the feedback mechanism still affects any changes in the plant. Same mechanism that compensates for disturbances. As with a closed loop system, as the effects of disturbances and plant changes are minimized, it would give us a more accurate output as compared to an open loop system. Any errors, any disturbances, any changes in the plant must be compensated manually through the change in input. Unlike with a closed loop system, that the feedback or the sensor feedback automatically compensate for those changes. As such, if no one is carefully watching an open loop system, its output would be less accurate. But of course, closed loop systems have also its disadvantages compared to an open loop system. The addition of a feedback mechanism and the adjustment in the controller to be able to detect the difference between the input or the reference input from the sensor or the output would require additional components, which in turn would cost more. This also makes a closed loop system more complex than an open loop system. Depending on the requirements or the objectives of the control design, open loop systems could be used as opposed to a closed loop system. If the objectives require it to be much more simpler compared to what is being designed. Another disadvantage of a closed loop system is that when a closed loop system is improperly designed, it can cause instability in the system. Remember that a closed loop system compensates for any differences from the output compared to the desired output. Sometimes when it compensates, it overshoots its desired output, and then it compensates again. Depending on the design, it could have or it could overshoot infinitely. Or in worst cases, cause great instability, as the second overshoot could be greater than the first overshoot, giving rise to a very unstable system. But when a closed loop system is designed properly, it is highly beneficial for certain or for most complex systems. We have a topic dedicated to detecting instability in a closed loop system. But how do we design a good control system? Maybe it a closed loop or an open loop system. In any engineering endeavor, design is of number one priority. So control systems follow or generally follow this design flowchart to be able to determine or to be able to create a good control system. The first part of this flowchart is to determine the control objectives. Control objectives is of course dictated by what is the needed output of the control system. We have said many times already that control system is all about the output. And as such, any objectives should revolve around the desired output. Some examples of control system design objectives could include a zero steady state error. The steady state is defined as the final output or the steady state output of the control system. In a refrigerator or an air conditioning system, this could be the final temperature as set by the controller. In an elevator, this could be the floor in which the button was selected. As much as possible, we do not want to have any steady state error, but there are systems that can actually acquire or accept a percentage state error. Another objective is the minimal time to reach that said steady state error, or the speed to reach the final or desired output. But we have to be careful that sometimes, especially in physical systems, we do not want to speed it up quite a lot. Imagine an elevator that goes from 0 to 60 in a fraction of a second just to get you to your floor of choice. As I only can imagine, that would be quite horrific, akin to riding a roller coaster. The G-forces and the abrupt starting and stopping of the system could also not just damage or injure a person, but could increase the wear and tear of the elevator system. Another objective could be minimizing the percent overshoot. We can use an elevator as an example. Most of the time, you would notice when you are in an elevator, the floor of the elevator is equal to the floor that you're going to, meaning there is almost minimal difference between where you're standing on the elevator from and when you're stepping out for the zero state error. But most of the time, to prevent overshoots in elevators, it would slow down before reaching the final floor or the floor that was selected. If for some reason it was speeding up, the momentum would carry you upwards, causing you or causing the elevator to overshoot or have a system or have the floor higher or the elevator floor higher than the desired floor. Once the objectives have been carefully stated and dictated, we will now go to modeling. But before I forget, the objectives, in order to be correct, must go through a rigorous process of communication with the users and the owners of the system, not just the one that will design it. Without that careful communication with the client, we may misinterpret what they want us to do. And a failed objective would also result automatically into a failed design. Now, once the objectives have been dictated and approved and evaluated, the next step is modeling. Modeling in control systems require us to transform physical systems into its equivalent mathematical equation. Part of our discussion, or what we'll be doing in control systems, is to transform physical systems into its appropriate mathematical equations. But we will be focusing on electrical quantities. Once the model or the mathematical model has been created, it is time to verify the model. Verification of the model or the mathematical equation is usually done through software simulation, and it is used to check if the response of the model is similar to actual responses. A requirement for model verification is we know at least of a certain output given a specific input. So we need something to compare to, as without that, we won't be able to successfully verify our mathematical equation. Once we have verified that our created model is close to or equal to the actual response, then it is time to develop the controller itself. The development of the controller and compensator actually rests upon the experience of the control designer. The more experience he or she has, the quicker and the better the control architecture would be. Unfortunately, even with the most experienced control engineers, there would be some form of unknowns that needs to be taken care of in a controller. Through the control design and by using other mathematical methods and other simulations, we need to compute for those unknown controller parameters. If we are unable to determine those unknown controller parameters, then we won't be able to create our desired controller that would give us satisfactory satisfactory completion or compliance of the control objectives. Once the development and the design of the controller has been done, the last step is to verify the controller. It is assumed that all parameters have been taken care of or has been computed, and the controller would be verified either through simulation, again, or through building a prototype and testing that prototype. If for some reason the controller does not meet the control objectives, then the system engineer or the controller engineer have to go back to previous steps. In extreme cases, they may have to go back to the first step. In order to avoid going back to the first initial steps and wasting time and money, the first steps have to be done carefully and correctly. If done correctly, even if there is some sort of problems with the controller verification, you would only go back at worst to control architecture design, but most experienced control engineers only need to go back and verify the unknown controller parameters. And with that, I bid you farewell. If you have any questions, kindly leave it at the comment section below. Don't forget to like and subscribe. And thank you very much.